So moving on with our systems in Unit C, this time we're going to talk about linear inequalities. So we've been dealing a lot with these realities of consistent, dependent, and inconsistent. We're going to carry on and talk about what happens when they are not just equations, but inequalities. And so we've dealt with graphing linear inequalities before, where we had boundary lines that were dotted or solid, right? Remembering the solid lines had the equal to part of them. And then we had this business of the half plane. And so shading the half plane was important when we were graphing just linear inequalities. But now with systems of inequalities, we're going to see where those half planes intersect, because that's actually going to be the solution to our systems of inequalities. In all of our linear inequalities, we're going to have consistent linear inequalities, so they will intersect. And you can imagine here that if we had a half plane for this first equation that was below the line, and maybe for the other equation that was also below the line, the actual solution for this is going to be where those two intersect. And so this region down here that, both of the half planes are overlapping, that's going to be what we're looking for in our answer for these linear inequalities. We're only going to solve them by graphing. We are not doing algebra with these ones. And so we will be able to draw those pictures and see where those planes intercept each other or overlap each other. So with these, I think that mx plus b is always a good place to start. So I'm going to start by putting both of these into mx plus b form. One thing to remember is the rule. It was switch the sign if you divide by a negative. So hopefully you're bringing that one forward with you from the last unit, right? Because that's going to be relevant as we move into these. You can subtract things. Fine, I didn't switch the sign there. But if you're dividing, then you do switch the sign. Okay, so my y-intercept is 0 and 4, and my slope would be a -1/1. So I'm going to go ahead and put this on the graph, kind of process it as I go. So down 1 and over 1, down 1 and over 1. This is going to be a dotted line at this point. Dotted lines are a little bit easier for me to draw accurately. Well, almost. And then this half plane shading business. So this half plane is going to be the y values are bigger than my line. And so up here is where my line or my y values are going to be bigger than my line. So I could shade this region as the half plane of that first linear equality in my system. Okay, so let's move on to the second one. So I'm going to start by subtracting x on both sides. I get -y is less than -x plus 2. Dividing by -1, enacting my rule, I'd have y is greater than x minus 2. So my y-intercept would be 0 and -2. My slope is going to be a +1/1. Let's put this on the graph. So there's my intercept, and my slope tells me up 1 and over 1, up 1 and over 1, up 1 and over 1. My boundary line is going to be dotted because I don't have an equal to part of my inequality sign. And then this half plane business. If you do have a highlighter, it's kind of fun to do it like this. When you can color in math, maybe that's good. If not, I don't know. I like it. So I see here that y is actually greater than my line. So that would be above my line. And so I could shade the half plane on this one. And really the key thing is where they overlap. So where these two overlap, this region right here, is actually the region of xy values that would make both equations true at the same time. If you want, you can take a test point on there and sub it in. It should make both of them true, right? Whatever you have should be greater than 4, and whatever you have should be less than 2. And that's how you could verify these ones, but sometimes that's harder than just seeing the image. So we're going to keep going with solving by graphing. Let me know if you want more information on verifying these ones. In these ones, same approach. I'm going to put them in mx plus b to put them on the graph. Remembering that rule, when you divide by the negative sign, you have to switch the inequality. Doing the interpretation of the y-intercept and the slope. So I'm going to put those points on there, up 2 over 2, up 2 over 2. And this is going to be a dotted boundary line. Kind of more like a dotted path. And then this business of the half plane, it says that y values are bigger than my line. That's going to be above my line. So all this region up here, oops, bigger than my line, right? I'm going to move on and do the graphing of the second inequality. So subtract x from both sides. I get y is less than negative x plus 3. Doing the interpretation of this, I'd get y-intercept of 0 and 3, and my slope of a negative 1 over 1. So putting that on the graph, 0 and 3, down 1 and over 1, down 1 and over 1, all the way. Again, this doesn't have an equal to sign of it, so or sign with it, so my boundary line is going to be dotted. And then I'd have to do this half plane business, right? I'm going to shade the region where y values are smaller than my line. I'm going to switch colors because you can see where the two kind of overlap. I'll make purple this time. So the y values are smaller than my line. So it'll be everything down here. And when we consider these two together, the answer to this is the region where those two half planes actually overlap. So this kind of quadrant, if you will, that sort of triangle over on the left there is where the XY coordinates that would make both of these inequalities true at the same time would lay. And so that's the answer to this system of linear inequalities. Trying a few more. If you want, you can go back to the notes key if you want to try this on your own. If you want to hear the kind of worked solutions and me hopefully catch if I've made any mistakes or whatever, or you want to listen to me make mistakes, keep the video playing and I'll go along. There's always some tricky ones near the end too. Remembering to switch the sign when you divide by that negative number. I like kind of doing these all the way because I find there's a lot of moving pieces, right? There's a lot of parts to them. For this one, again, I have a dotted boundary line. There we go, more or less. And then this half plane business. So the half plane, the y values are going to be smaller than my line. So I'm almost off here, but below the line is where those y values are smaller. So that would be relatively messy graphing of that first linear inequality. The second one, I'm going to do all the same stuff for. I would have that my y-intercept is 0 and 6, positive 6 this time, and my slope is a negative 1 over 1. Let's graph that. So I start at my point, down 1 over 1, down 1 over 1. So I've got it on there. My boundary line is going to be solid this time because that inequality has an equal to sign part of it. Now I'm going to switch to the highlighter and I'm going to highlight the half plane. So the half plane is where the y values are smaller than this line. And so remember, this was the line that I just drew, and everything over here below the line, oops, I can't keep up with my highlighting, is where that half plane would be shaded. And again, the answer to this is where those colors overlap, right? This region down here is where the xy values that make both of these equations true would lie. So we don't give a coordinate, it's still a consistent system, but because of this overlapping half plane, that's really how you give the answer to these systems. Several more to try. Again, I go to mx plus b form. Whoops. Remembering when you're dividing by a negative, you enact that rule of switching your sign. Watch your fraction math here. Watch your signs. And I'm going to give this the full treatment. I'm going to go all the way with this. So there's my y-intercept, and my slope tells me to go up 1 over 2, up 1 over 2, up 1 over 2. It's going to be a solid line here. Whoa, I hit every one of them. And now I'm going to shade the half plane. So the half plane tells me that the y values that are smaller than my line are what I'm going to color in. So that's below my line. I'm going to go back and do the second equation, putting it in mx plus b form. Divide by -2. Watch signs. It switches the inequality, that dividing by -2. My y-intercept for this one is going to be 0 and -6, and my slope is going to be a 3 over 2. So my y-intercept is down here at 0 and -6, and my instructions to the next line tells me to go up 3 and over 2. Up 3 over 2, and this is going to be a dotted line at this because I don't have an equal to part of my equation. Now the last part of this is shading the half plane. Really happy I found the highlighter option in this. I'll go yellow this time, maybe I'll make orange. So the y value is smaller than my line again. So it'd be everything here, which is below that line that I just drew. And if you can see where the two colors overlap, right, this is actually the region that represents the solution to this linear inequality. The next two are different looking equations. And so we can have horizontal and vertical lines. We can have regions of x and y. And so really these are just different looking. And so we can have x values smaller than 1. So we'd have a line at 1. And we'd have a line at 3. Whoops, they are solid lines because there's an equal to sign of them. And we could have y values at 2 and 5. And basically these inequality signs here are saying that x values is everything in between these two, and the y values is everything in between these two. So if I go for the highlighter for the x values, it's everything in between these two for the x values, right? And it's everything in between these two for the y's. So what we've done is make a nice like gingham or tartan or plaid thing here. The region in this square in the middle is where they both overlap. And so that would be the solution to this. Give this one a try. Again, they're just different looking equations, but that idea of where the regions overlap is what we're after for these. So, you know, which values make both of them true at the same time. So I'll draw mine. Oops, that is not a straight line. Use your imagination. And again, where the shaded regions overlap is the solution to these systems. So systems can be more than just two equations. When we were dealing with the algebraic approach and equations, we only ever dealt with two, but this is really throwing it all at us. And so these ones, what I'm going to do is put them in mx plus b form. And I'm going to work to get all of these on the graph. I'm going to shade each one's half plane, and really where they all overlap is the solution to this really big system. So this first equation, I'm going to subtract 2x on both sides. I get that y is less than or equal to negative 2x plus 5. That tells me, and I'm going to, well, I'll do it. Y-intercept is 0 and 5, and my slope is negative 2 over 1. Let's put this on the graph. So we've got 0 and 5, negative 2 over 1, negative 2 over 1. This is going to be a solid line at this point, or along these points. And the half plane that I'm shading here is going to be y values smaller than this line. So it'll be everything down here. Try and make this neat because there's going to be a lot going on with it. Oops. Oh, there we go. Okay, let's do the next one. So the next one, again with this, maybe I'll just write it out over here. So x minus y is less than 3. I'd subtract x from both sides. I get negative y is less than negative x plus 3. Divide by negative 1 on both sides. I get y is greater than x minus 3. That gives me an intercept of 0 and negative 3, and up 1 and over 1, up 1 over 1, all the way. This is going to be a dotted line at this point because there's no equal to sign in my inequality, and I had to switch the sign. So the half plane for this is going to be above, whoops, I got to switch colors. That doesn't help, does it? Above the line. So we can see the region starting to show that is defined, right? Or the purpley color is. Let's keep going on these, right? So we handled that one here. This x is greater than 1 is just a line at 1, greater than or equal to, sorry. And that means it's going to be over on this hand side of it. I don't know if I can keep going with the highlighter here. Maybe I'll switch to yellow. So we're looking for the x values that are greater. So if you can see, there's a little triangle in here that has had every highlighter color on it. Let's do the last one. So y is greater than or equal to a negative 2. So that means that I have a line at negative 2, and the y values are bigger than my line. So if you can imagine, it's everything above this line. Now, the answer to this is only where all of these things have been shaded. So I spared you the extra highlighter color, right? But everything above here would color over this little interior triangle. And that's the answer to this really complicated system of inequalities. Let's do the last one here. In both of these, I think it's important to take the time and put them in mx plus b form. So I'd end up with negative y less than or equal to negative 2x plus 6, subtracting 2x from both sides. The space on the page is terrible here. I'm dividing by negative 1, so that switches my sign. I'd have 2x minus 6. So putting this on the graph, you might be ready to drop that step of doing the interpretation. 0, negative 6 is my point, and this tells me to go up 2 and over 1. Up 2 over 1 is going to be a solid line at this point, or along these points. I keep saying that funny, sorry. Oops. More or less like that. And the last business, the shading of the half plane, is going to be the y values that are bigger than my line, or above my line. So it's everything on this half of my graph here. Okay, so let's move on to the next one. So the next one, I would subtract x on both sides, and I get y is less than negative x plus 5. So putting that on the graph, I have an intercept of 0 and 5, and a slope of down 1 and over 1. It's going to be a dotted line at this point. or along these points. And shading the half plane, I'm going to pick all the values of x that are smaller than my line or below my line. So it's everything here. And you can see where I'm making the orange color, right? Where the pink and the yellow overlap. So doing the last two, this says that x greater than or equal to 0 is a vertical line at x equaling 0. And it's saying that x, everything on the right-hand side, everything that's bigger. So we're kind of all positive values of x, if you will. I'm going to pick blue for that. So it's everything over here. So far we're developing this region that is, shaded with everything kind of going to be a bit of a mud color in the middle. And I'll do the last one. So y is greater than 0 as well. So that's a line at 0. And greater than 0 gives me this funky little shape right here. It's no longer a triangle. I don't know exactly what you'd call it, but that region on the graph is where the xy values that make this system true is really found. These are all called constraints on a system, and these are really common constraints. The last section of Unit C is going to be more practical applications of this, where we can talk about these being regions of optimization, regions of possibility for things that are defined by linear inequalities. And so these constraints being above 0 in both the x and the y is really common. So you can't have a negative number of workers. You can't have a negative number of products, right? And so in application, these are really common constraints as we move into our last section in Unit C, which are these optimization problems.